Today, we are going to learn about the principles of mobile phone charger circuits. The mobile phone charger converts AC mains to 5 volts stable voltage for charging the cell phone. How does that small charger produce 5 VDC from our 220 VAC main power supply? The traditional way to convert the AC to DC is use a linear transformer to step down the voltage to desired level and then convert the AC to DC using a bridge rectifier. Then smooth the output using a capacitor. Finally, use a regulator to get exact DC voltage. You can learn more details about how to convert AC to DC using a traditional linear converter by the link in the description. But the problem with these kinds of power supplies is, even though they can convert the AC to desired DC, the efficiency is low. It normally wastes a lot of energy as heat, and moreover, they are heavy and large in size. That is why those are unfit for traveling chargers. One of the main differences between these power supplies is the size of the transformer used. In traditional linear power supplies, the transformer is a large and heavy component. On the other hand, the phone charger contains a much smaller transformer. Let's discuss how this is achieved. The concept of Faraday's law of electromagnetic induction states that a changing magnetic flux through a coil of wire induces a voltage in the coil. For a transformer, the root mean square of induced voltage at a winding can be calculated using the supply frequency, number of turns, core cross-sectional area, and peak magnetic flux density. I'm not going to explain the math in depth here. Simply, in a transformer, the voltage of primary coil is proportional to the frequency, the number of turns and area of the core. Traditional linear transformers operate at the frequency of the mains AC, which is typically 50 to 60 Hz depending on the region. To achieve maximum power output and efficiency in these transformers, a larger core and a higher number of turns in the windings are required. However, this results in larger and heavier transformers. But we can solve this problem if we have a way to increase the frequency of the current. Then we can use small coils to the transformer and reduce its size heavily. These kinds of power supplies are called switch-mode power supplies, or SMPS. Let's see how this SMPS works. Initially, the 230-volt AC input signal from the source is provided to the input rectifier and filter circuit. This converts the AC to rippled DC. Then the unregulated DC output is fed to the power transistor that acts as a high-frequency switch. It converts the DC into a very high-frequency square wave. The high-frequency DC is stepped down into low voltage, probably 5 volt, by a flyback high-frequency transformer. You may wonder how the DC is stepped down using a transformer, but keep in mind this is not a pure DC. It changes the voltage at very high frequency. Low-voltage DC is further provided as input to the output filter unit. This simply filters out the unwanted residuals from the signal in order to provide a regulated DC signal as the output. The feedback path and control circuits are used to control the output DC supply. Let's recap the key steps of this circuit's operation. The first step is to rectify the AC voltage using a diode bridge rectifier. This converts the AC voltage into a pulsating DC voltage, but it does not reduce the voltage. In fact, the peak voltage after rectification is higher than the AC voltage. The heart of the SMPS is the high-frequency generator, which operates at a much higher frequency than the mains AC frequency. This generator typically uses a transistor-based oscillator circuit to produce the high-frequency switching. The transistor T1 is connected to the primary coil of a small transformer. The resistor at the base of T1 partially turns it on, allowing only a small current to flow from collector to emitter. There is a small secondary winding S1 placed near the primary coil. The ripples in the primary coil induce a small current in S1. This induced current charges the capacitor C1 connected to S1 and then turns on T1 completely, allowing a high current to flow through the primary winding. As a result of the high current flowing through the primary winding, a high voltage is induced in the secondary winding S2 of the transformer. Another transistor T2 is connected to the circuit. When the voltage at S1 is low, T2 remains in the off state. When the voltage at S1 becomes high, T2 turns on, which pulls the base of T1 to 0 volts and turns T1 off. With T1 turned off, no current flows through the primary coil, causing no current to flow in S1. As a result, the base of T2 becomes low, turning T2 off as well. Now again, the resistor at the base of T1 partially turns it on, allowing only a small current to flow from collector to emitter. Then the cycle repeats. Let's have more clear view. Pay attention to the primary voltage shown by the graph. Due to this struggle between T1 and T2, the voltage of the primary coil increases and decreases rapidly. Likewise, the frequency of the primary winding's voltage is increased up to about 100 kHz. Next, move on to the final parts of the circuit. Now the transformer steps down this high-frequency DC to desired level. Next is the output filter. It smooths the high-frequency step-down DC by reducing voltage variations. Finally, the feedback path. It mainly consists of a Zener diode and optocoupler. If the output voltage of the filter circuit is more than 5 volts, the Zener diode passes the current and turns on the optocoupler. Then it passes the current to the base of T2 and make it turn on. This again turns off the T1 and stop the current goes to the primary of the transformer, which reduce the output voltage. The continuous high-frequency switching, along with the transformer action, allows for efficient energy transfer and voltage regulation in the SMPS. This process enables the conversion of the higher DC voltage from the rectifier to the desired lower and stable DC voltage required for charging electronic devices like mobile phones. The switching action, along with the feedback control mechanism, ensures that the output voltage is regulated accurately, despite fluctuations in input voltage or load conditions. This switching operation allows for the use of smaller components, making SMPS compact, efficient, and suitable for a wide range of electronic devices and applications.